posting. Let's find some antiderivatives. Let's say, and again, we're going to use the notation with the integral symbol, just believing that yes, that means antiderivative. So let's find the antiderivative of, say, oh, that's interesting. Oh, I see. Okay, sure. Let's do something like this. X to the fourth plus the fourth root of x to the fifth plus cosecant squared x dx. Before we do this, there is one thing we should do. And this is kind of the general statement I want to make is we should definitely be simplifying things before we anti-differentiate them. So this fourth root of x to the fifth, I should rewrite as x to the 5/4 power. So then for these parts, we're just going to use the anti-power rule. The antiderivative of x to the fourth is x to the fifth divided by 5. The antiderivative of x to the 5/4, again, we're just using the same rule that we're adding 1 to the power and dividing by the new power. So we're going to get x to the, let's see, 5/4 plus 4/4, which is 1, is 9/4. And dividing by 9/4 is equivalent to multiplying by 4/9. And then the antiderivative of cosecant squared is negative cotangent of x. Because the derivative of cotangent is negative cosecant squared. Plus c. Gotta have that plus c. Let's look at a couple more. Let's find the antiderivative of, say, I don't know. Yeah, why not? Where'd you go? Yeah, I like where it is. I'm going to write this in a slightly different way. I'm going to write this as 1 plus 3x over x squared plus 9 over 1 plus x squared. So both of them, well, this first part requires a little bit of extra work. We really should break this up as two fractions. We can write it as 1 over x squared plus 3x over x squared. And this 9 over 1 plus x squared, there's nothing you can really do with that. You're kind of stuck with 9 over 1 plus x squared. And then we're going to rewrite these. Now, you might have a different opinion about what I'm going to do here. So I'm going to write this as the antiderivative of x to the minus second. And then 3x over x squared, I can write as 3 over x, or 3 times 1 over x. Now, usually, yeah, totally. The 9 over 1 plus x squared is the derivative of an inverse trig function for sure. Usually for when I'm writing things as powers of x, almost without a doubt, I like to write it as x to a power. This is kind of the one exception. I usually prefer to write this as 1 over x to remind me that its antiderivative is the natural log of the absolute value of x. You could also write it as x to the minus first, but it's the same either way. I just feel like this way makes me remember it better. And then, yeah, I'm going to write this as 9 times 1 over 1 plus x squared dx. So then the antiderivative of x to the negative second is x to the negative first divided by negative 1. The constant multiples just hang out. The antiderivative of 1 over x is the natural log of the absolute value of x. And the antiderivative of 1 over 1 plus x squared is the inverse tangent or the arc tangent of x plus c. All right, let's look at a couple other things. Yeah, let's look at those.
Professor?
Oh, yeah, sorry, let me turn my volume here. Go ahead.
I have a quick question. The only thing I got kind of confused on is the second part, the 3x over x squared. So can you repeat that whole process again? I kind of.
So I rewrote 3x over x squared as 3 times 1 over x. You could also write it as 3 times x to the negative 1. For any other power of x, we know that the antiderivative of x to the n is x to the n plus 1 divided by n plus 1. But that doesn't work if n is equal to negative 1. For the antiderivative of x to the negative 1, which I usually prefer to write as the antiderivative of 1 over x. The antiderivative of that is the natural log of the absolute value of x. I'm not writing the plus c's just because I don't have the room.
Mm-hmm.
That's all that's happening there. So we're just remembering, oh yeah, we know that the derivative of the natural log of x is 1 over x. So the antiderivative of 1 over x is, in fact, the natural log of absolute value of x. So all I was really saying there is that I prefer to write it as 1 over x because it's a little more easy for me to remember that the antiderivative of 1 over x is the natural log of the absolute value of x.
Okay, so the only thing I'm just kind of confused on is why 1 over x? I'm just confused. Like, where did the x squared go? And
well, so I simplified this, right? I have a 3x over x squared.
Oh yeah, you got rid of. Okay, yeah, never mind. I completely forgot about that for sure. Thank you.
To answer Adrel, I hope I'm saying your name correctly. I get the 9 arc tangent from the fact that I had 9 over 1 plus x squared. I factored out the 9 to make it 9 times 1 over 1 plus x squared. And then we do kind of have to just memorize that the antiderivative of 1 over 1 plus x squared is the arc tangent of x, or the inverse tangent of x. Yeah, you're right, Katie. So just to kind of remind you of them again, because they are going to show up. These first two are the ones that show up the most. The antiderivative of 1 over the square root of 1 minus x squared dx is the arc sine of x plus c, or if you prefer, the inverse sine of x. Right, same meaning, just different notation. The integral of 1 over 1 plus x squared dx is the arc tangent of x, or the inverse tangent of x. And then the last one, which probably shows up less, but you should still be aware of, is that the integral of 1 over x times the square root of x squared minus 1 dx is the arc secant of x plus c, or the inverse secant of x plus c. Sometimes there's an absolute value on the x there. I wouldn't sweat that too much. Usually people will kind of help with that if there's an issue. Okay. So actually that brings up some good questions. So we don't know yet how to anti-differentiate a lot of things, but we can still ask some questions about whether we know what an antiderivative of a thing is. Here's what I mean. So here's what I want to ask. Is the antiderivative of tangent times secant squared theta, tangent theta times secant squared theta, d theta, is that equal to secant cubed theta over 3 plus c? So one way you could check, sorry, just one second. I have one thing open. I have Discord open somewhere, and it's like looping. It's annoying. There we go. Okay, great. So eventually we will actually learn how to anti-differentiate this. It's a pretty straightforward process once we learn how to do it. But if we don't know the process for anti-differentiating anything, but you're asking, is that the answer? Well, one way to check is if the antiderivative is equal to that, then it should also be true that the derivative of that, d theta, right, so differentiating with respect to the variable theta, of secant cubed theta over 3, if this is the antiderivative, if this is the antiderivative of this, then the derivative of that should equal this. So is that equal to tangent theta times secant squared theta? I don't know, let's find out. Because we definitely know how to take derivatives. So I'm going to write this as 1/3 times secant cubed theta. Or better, 1/3 of secant theta quantity cubed. My cat's trying to escape. 1 second, let me let her out. Go ahead, you can leave. Yes. Be gone. Okay, great. So let's find out here. I get 1/3. The derivative of some stuff cubed is 3 times your stuff squared times the derivative of your stuff. We're not so much proving something, we're checking to see, is the integral of tangent theta secant squared theta equal to secant cubed theta over 3? And since we don't know how to integrate this, what we're going to do is we're going to say, well, if I differentiate this and it's equal to that, then it's true. If it's not, it's not. So let's see. The derivative of 1/3 secant cubed is 1/3 times 3 times my stuff squared times the derivative of my stuff. And the derivative of secant is secant theta times tangent theta. So the 3's cancel. I get secant squared times another secant, which is secant cubed theta times tangent theta. So no, it's not. The integral of tangent theta secant squared theta is not equal to secant cubed over 3, because the derivative of secant cubed over 3 is equal to tangent times secant cubed, not tangent times secant squared. So if you're ever checking to see if someone says, is the antiderivative of this function this other function? One way to check is just check, is the derivative of the other function equal to the original thing you're trying to differentiate? If it is, then it is. If it isn't, then it isn't. Let's do one more. Let's do a funky looking one. So, let's see what have I got here. I want to ask, is the antiderivative of arc tangent of x divided by x squared equal to something that looks pretty wonky, the natural log of x minus 1/2 the natural log of 1 plus x squared minus the inverse, or let's use the arc tangent of x over x plus c. Okay. Is that equal to that? Well, we're going to check. We're going to take the derivative. So let's take the derivative of the natural log of x minus 1/2 the natural log of 1 plus x squared minus arc tangent of x over x plus c. For those of you just joining, we are checking to see if the integral of arc tangent of x over x squared is equal to all this by taking the derivative of all this and seeing if we get arc tangent of x over x. Because we don't yet, although we will someday, have the tools to integrate arc tangent of x over x squared, but we will eventually. So let's find out. So this derivative is 1 over x minus, let's see, 1/2 times the derivative of the natural log of 1 plus x squared is 1 over my stuff times the derivative of my stuff. Okay. And then the derivative of arc tangent x over x, we're going to have to use the quotient rule. So it's going to be bottom times the derivative of the top. The derivative of the arc tangent of x is 1 over 1 plus x squared minus the top times the derivative of the bottom, which is just the derivative of x is 1, all divided by x squared. That's looking pretty funky. And then plus 0. So let's see here. Let's do some stuff. I can cancel a 2 here and a 2 here. So I've got, let's see, 1 over x minus x over 1 plus x squared. And eventually I'm hoping to get to this. So here's what I should do. I should break this apart into 2 different fractions. Why? Well, because I see an arctangent x over x squared, and that's what I'm hoping to end up with. So I probably need those to separate out anyway. So here's what I've got. I've got minus x times 1 over 1 plus x squared. Okay, yeah, sure. That's going to be interesting. Over x squared, that's kind of terrible. And then minus a minus is plus arc tangent of x over x squared. So for this to work out, I need all of these things to cancel. Well, let's see. I can get a common denominator. I can say that So if I look at this, it's actually, in fact, let me rewrite it. So let's get some common denominators. So I'm going to multiply this by 1 plus x squared over 1 plus x squared. So I have 1 plus x squared over x times 1 plus x squared. Minus, here I'm going to multiply by x over x. So I have x times x over x times 1 plus x squared. Minus, and here, I actually already have the right denominator. Because what I really have is, well, I can cancel an x here and an x here. And then I basically have 1 over 1 plus x squared divided by x. So 1 over 1 plus x squared dividing by x is multiplying by 1 over x. Okay, plus arctangent of x over x squared. But now look, I really wish I had a little bit more room. Sure, I can squeeze this in down here. It's going to be a little tight. So look what I've got. These three fractions all have the same denominator. So I can write them as one fraction. The denominator is x times 1 plus x squared. And the numerator is 1 plus x squared minus x squared minus 1. Oh, look, that all cancels. So that's 0. And then we get plus arctangent of x over x squared. So I know it's a little hard to see. I apologize. Yeah, I got a common denominator. But look what happened. So we took the derivative of this hot mess over here, and after doing some work, we ended up getting the derivative of this was equal to the arctangent of x over x squared. Which means that the antiderivative of the arctangent of x over x squared is in fact natural log of x minus 1/2 natural log of 1 plus x squared minus arctangent of x over x plus c. So if someone ever asks you, is this antiderivative equal to this other function, you can always check by taking the derivative of the other function.
Wait, James, I have a quick question.
Go ahead.
So for like when you got everything together because of the common denominator, since we have a 0 on top, the whole thing just goes to 0?
Right, because 0 divided by anything, well, 0 divided by anything that's not 0 is 0.
Okay, yeah. Yeah, I just wanted to clarify. Thank you, James.
Yeah. So let's go ahead and move on. Let's look at some initial value problems. So let's say we are given the following. We're given that dr d theta is equal to cosine of pi theta. So right, we're thinking that r is a function of theta, that the radius is a function of the angle. And we are also given that r of 0 is equal to 1. We would like to find r as a function of theta. Okay. So if you're given a derivative and you want the original function, we have to anti-differentiate. What's the antiderivative of cosine? Okay. I guess I can fill in the blank.
Was it antiderivative again?
Yes, what's the antiderivative of cosine?
Would that just be sine?
Yeah, totally. So the antiderivative of cosine of theta is sine of theta. The antiderivative of cosine of pi theta is going to be almost sine of pi theta. But that's not quite right. What do I need still? What do I need to divide by? Well, think about it this way.
Would it be pi?
Yeah. If we take the derivative of sine of pi theta, you're going to get cosine of your stuff times the derivative of your stuff, which is pi. Right. So we have to divide by the constant. Just want to make sure you guys remember that from last time. It's going to come up a lot. So I really want to stress, right? Like if you're anti-differentiating something and you have something multiplying your variable, you're almost always dividing by that constant that's multiplying your variable. happens all the time. Okay, so we've got this, but now we also have to deal with this initial condition. So basically, if you have an initial value problem, the idea is you're supposed to solve for the plus c. So if I plug in 0, r of 0 is sine of pi times 0 over pi plus c, and that's supposed to equal to 1. Sine of 0 is 0, so we get 0 plus c equal to 1, so c is 1. Now we're not quite done, although we're pretty much done. Technically, the solution here is what the actual function is. So we have to go back and say, oh, r of theta is sine of pi theta divided by pi plus the constant which we solved for. That's our actual final answer. So the idea of this comes up in lots of motion problems, where you're given some knowledge about acceleration or velocity, and you're asked to find the position, and you're given some initial conditions, like what the initial velocity or the initial position might be. This specifically applies to the airplane problem that's in Morris's kind of, I mean, it's not exactly that problem, but that's kind of the idea there, is that you're given some information and asked to figure out some other stuff. So let's take a look at this example. A rocket takes off with a constant acceleration I think what do I have here? 20 meters per second squared. How high is it after 1 minute? Okay, well, we need to figure some things out. So the airplane problem. I did write something about the airplane problem on the discussion, so take a look at that for sure. So we're given constant acceleration and we're asked to figure out how high is that moment. We know that the initial velocity is 0, right? If we're talking about when it's taking off, starting off with velocity of 0. And the initial position, or the initial, I would probably use height instead of position here, just because it is going up. The initial height is also 0. And we know that acceleration, which is the derivative of velocity, and I prefer this notation, is equal to 20 meters per second squared. So this is going to allow me to find an equation for the velocity at time t. So I anti-differentiate this. V of t is equal to 20t plus a constant. And that constant is actually the initial velocity, because if you plug in 0 for t, you get 20 times 0 plus the constant. So the constant that you get here is literally v naught, which we know is 0. So now we have the velocity as a function of time. It's equal to 20t. And we want to know the position as a function of time. So position is a function of time. Well, position is the derivative, the derivative of position is equal to velocity. So I want to find the position, I need to anti-differentiate the velocity. So the antiderivative of 20t is going to be 20t squared over 2 plus another constant. You can use the same letter c, you can call it k, it doesn't really matter. So let's see, that's 10t squared plus k. And since the initial height was also 0, we can plug in 0 for the time, right? The height at time 0 is equal to 0. So when we plug in 0 for t, we get 0 plus k has to equal 0. So we end up getting k being 0 as well. So the height after t seconds is equal to 10t squared. So then we could ask, how high is it when after 1 minute. So we're setting t equal to 60 seconds. So the height at 60 seconds is going to be 10 times 60 squared, which is going to be 36,000. Sorry, meters, those in meters. Yeah, definitely. Also, the velocity after 60 seconds is what? Well, it's 20 times 60, so that's going to be 1,200 meters per second. So we can work backwards for just a second here. Let's pretend like, no, I don't know if we have to pretend. Let me think here. In the airplane problem, you're given like the velocities and you're not actually given, no, but you're still given, I actually gave you guys less information here. I guess you're not given the acceleration in the airplane problem. So I could have, let's pretend like let's back up for just a second. I'm going to pretend like, instead of telling you that the acceleration was 20 meters per second, let's pretend like we didn't know that. So let's say that I'm telling you there's constant acceleration, and instead of telling you what the acceleration is, I'm going to tell you that the velocity at time 0 is 0 meters per second, and the velocity at 60 seconds later is 1,200 meters per second. So here's the thing. If you know that the acceleration is constant, and you know that the velocity, the velocity at 2 different times, you can find the acceleration. You can just say, well, how much did the velocity change by? Well, the velocity changed by 1,200 meters per second. 1,200 minus 0 is 1,200. And the acceleration, sorry, the time changed by 20 seconds. 1,200 divided by 20 is 60. Is it 60? Yeah. I'm like, is that right? Yeah. It's 60 meters per second per second. So, right, if you're given that kind of information, you can find the acceleration and then work through this whole same process. So, like, okay, I know the acceleration. I anti-differentiate that to get the velocity equation. Velocity is a function of time. And then we can anti-differentiate that again to figure out the position or how far the plane has gone. So there's a few more little details in there that you have to look at. I would definitely recommend looking at the discussion post that someone asked me about that I responded to. It's definitely manageable though.
Oh, James, I have a question.
Yeah.
How did you figure out once again that the change in time was 20 seconds?
It was given. So oh sorry, actually no, I apologize. Ooh, I made a little mistake there. I got my numbers interpolated. So the change in time wasn't 20 seconds. The change in time was how many seconds?
60.
Right. Sorry about that. Yeah, good observation there. So the change in time was 60 seconds, and then 1,200 divided by 60 gives us the acceleration that was 20 that I erased. So this is 20 meters per second squared. Sorry about that.
And yeah. that would be the answer if they would have asked us for like what's the acceleration at that time.
Right.
Or,
well, and so we're given that the acceleration is constant. So that's why we're allowed to kind of do this. Say, oh no, if I know the acceleration over any time period, I know that's the acceleration because I'm being told it's a constant acceleration.
okay, and then from there we could just backtrack and done like to find v of t and h of t. Okay.
Right. So once we use this information, these two different velocities at specific times, and the fact that it's a constant acceleration, then we can get the acceleration, then we can backtrack and get the velocity, then we can backtrack and get the position. Questions? All right, let's see, do I have anything else to say about that? So I think it's probably pertinent to move towards the next section, section 5.1, talking about estimating the area under curves and kind of all that jazz. So I will warn you all, this part of your class can be a little bit tedious. It's just not that it's not interesting. It's certainly there's kind of a lot of important mathematics here, but there's a lot of tiny little details that we have to actually pay particular attention to. So let's be very careful with our work. So let's start off with this problem. We're going to try to estimate the area under f of x equal to the square root of x on the interval from 0 to 16 using what we're going to call a regular partition of 4 rectangles. And yeah, there's a couple things I need to mention. So most of the time when I've seen people teach this class or taught this class, people usually talk about using right endpoints versus left endpoints. But I see that Schulten's, and I didn't know this from Morris, but I feel like his problems are the same. They're talking more about upper limits versus, or upper, what's the word I'm looking for here? Upper sums versus lower sums. Not quite balanced, upper sums versus lower sums. And those ideas are not exactly the same. So I will have to clarify that, which is fine. So the regular partition, just meaning I'm going to break up the interval from 0 to 16 into 4 equal partitions or lengths. Let's draw the thing. Let's say here's 16. We know we're going to break it up into 4 equal sections. And here's my square root function, which, okay, it's not going to be, this is not going to be quite the scale. That's fine. And I'm trying to estimate the area under this thing. Now, in this particular example, if I want to do the upper sum, I would use the right endpoints, because the right endpoint of each of these subintervals is the one that's the highest value of the function. So if I was going to do, and let me see what notation she's using here, just to kind of this. Sure, that's fine. Yeah, I just want to see, I want to make sure that, okay, yeah. So the way I would probably write this is I would write it as R4, because I'm using right endpoints with 4 subintervals, but at least Schulten's in her class is writing this as U4, because she's finding the upper sum using 4 subintervals. I want to be very, very clear. These are not always the same, meaning right endpoints don't always give you the upper sum. They do give you the upper sum if your function is increasing. But if your function is decreasing, actually the left endpoints give you the upper sum. And if it's doing something where it changes, then you can't pick one endpoint consistently and get what you want. It's kind of annoying. All right, so let's see what we've got here. I broke this up into 4 equal subsections. That's one thing here. That's not what I want. There we go. And so what I'm going to find here is that my delta x, right, the width of each subinterval, is equal to my total width, 16 minus 0, divided by the number of subintervals, which is going to be 4. So this here is my delta x. This here is my delta x. Right? Each of these subintervals has a length, or I should really say a width of delta x. And then I'm going to find the area of the rectangle by using the right endpoint. So this right endpoint is going to give me the height of the rectangle. So there's my rectangle. So this is going to equal my first base, which is delta x, times my first height, which is my function evaluated at that point right there. And then the next one, I'm using this right endpoint. Saying, okay, there's a rectangle. And I'm going to get base times height. Same deal over here. I can kind of switch back and forth. That rectangle, the area is going to be delta x times f of 12, base times height. And finally, this last rectangle here is going to be, again, base times height. So again, the idea here is that we are estimating the area under this curve. Now, clearly it's going to be an overestimate because the area of the rectangles is bigger than the area of the under the curveness. That's okay, we're just estimating. So in this particular example, this is going to be 4. And yeah, I really would like to factor out my 4, where I can let's write it. It's going to be delta x times f of 4 plus f of 8 plus f of 12 plus f of 16. So you can always factor out your delta x, which is the width of your subinterval, as long as they're all the same. And then we can plug it in. Delta x is 4. F of 4 is the square root of 4 plus the square root of 8 plus the square root of 12 plus the square root of 16. I don't so much care exactly what that is, but if you, and I didn't actually grab a calculator, so I suppose I should approximate it here. Let's see, we're going to get about, let's find out. Square root of 4, which is this. I just wrote square root of 4 on my calculator. I don't feel excellent about that. I know the square root of 4 is 2. You just kind of get in the mode sometimes. Square root of 8 is a little bit harder. Plus the square root of 12. Plus the square root of 16, yes, is 4, James. Times 4. That's going to be approximately 49.17. And this is an overestimate. I see a question there. What if you're not given a function but a table and no interval? We'll talk about that. Yeah, I think I know. I believe. Well, I'll try and grab a practice problem, but I think I know what you mean. We'll get there. On the other hand, we could also have used the left endpoints. So same picture.
James, I have a good question.
Yeah.
Is it more favorable to use the midpoints?
What do you mean by favorable?
When like we're taking the average?
Sure, but so are you saying it's more favorable because it gives us a better estimate?
Yes.
So I would say yes, the midpoints give you a better estimate generally. Here's the real truth though. We don't really care about this estimating stuff. It's not that we don't care, it's that the idea is that these estimates are going to lead us to a way to actually calculate the value exactly. And so what ends up happening is we end up taking our approximating quantity and then taking the limit of that. And although the midpoints do give you the better approximation if you're actually finding an approximation, no matter which you use, the midpoints, upper sums, lower sums, right endpoints, left endpoints, doesn't matter which you use, if you take the limit of any of those, you end up getting the right value. And so what we see in practice is that we usually prefer, at least I prefer, and most people prefer, to use the right endpoints because they're the least complicated to work with.
Okay, thank you, James.
You're welcome. Eric, as far as your question about whether or not we should write as an under or overestimate, if it's clear, it's good to at least think about. But sometimes if your function isn't always increasing or always decreasing, it's not going to be super clear if you have an over or an underestimate. And that's even more true if you're using midpoints, right? If you're using midpoints, it's really not clear if you've got an over or an underestimate. You might be able to guess here, but it's not always clear. So doing the same thing here, if I use left endpoints, So here's my left endpoint that has a height of 0. Okay, there's my first rectangle. It's not very exciting. Here's my second rectangle with a height of f of 4. I gotta start writing the area. So this is my left endpoint estimate using 4 intervals, or my, I don't remember what notation Professor Schulten's used. She also used L. So this is where notation could get confusing. I'm using L to mean left, and she's using L to mean lower. And yes, in this example, they're the same, but in a different example, they would be different. So just be aware that there are different notations for this stuff, and they can mean different things. And I'll try and maybe I'll try and stick with using upper and lower, since is that what Morris is also doing? Is Morris also using upper and lower? Nobody knows. That's all right. So I've got the area of this rectangle, which is 0. The area of this rectangle, which is the base times the height. The area of this rectangle, which again is the base times the height. And the area of this rectangle, which again is the base times the height. And calculating that, let's see. We get 0 plus 4 times the square root of 4 plus 4 times the square root of 8 plus 4. I could have factored out the 4 times the square root of 12, which is 4 times 0 plus 2 plus the square root of 8 plus the square root of 12, which is approximately, what have we got there? 33 point, doesn't really matter, 1/7. Yeah, this is definitely, so this is definitely lower. It's also left. And this is an underestimate. It should be the case that if you're finding the upper sum, it's an overestimate. Finding the lower sum, it's an underestimate. But let me give a little more context here. I guess we could also do it using midpoints, right? We could say, so this is where my picture's gonna start to get, yeah, let me make this one a little extra by doing the midpoints here as well. Grab a different colored pen, try to do this. So I use the midpoints, which are here. Here, this pen is not great. Here and here. Then our midpoint formula using 4 intervals is going to be, well, look, so this first rectangle, the base is still 4, but the height now is going to be given by that. I'm going to factor out the 4 because I know I'm going to be multiplying each of my rectangles having a base of 4. My second rectangle, base of 4, height of f of 6. So I get f of 2, f of 6. My third rectangle has a height of f of 10. My last rectangle has a height of f of 14. So this would be equal to 4 times the square root of 2 plus the square root of 6 plus the square root of 10 plus the square root of 14, which is approximately a number which I don't have calculated ahead of time because I forgot to do it. So okay, square root of 2, I love this calculator, plus square root of 6, it's all right, plus square root of 10, plus square root of 14, all times 4, gives us approximately 43.07. Is this an over and underestimate? It's hard to know, right? Are we under by more or are we over by more? I don't really know, right? It's hard to know. And it's usually not super duper clear when you have midpoints if you have an over and underestimate. And then you could even use a non-regular partition, meaning you could have different lengths. So here's actually kind of one last nice example. So here's a non-regular partition. Into 4 intervals, sub-intervals, I should say. So I'm going to do it like this. I'm going to say my points are 1, 4, 9, 16. Those are the points I'm going to use to find the heights at. So those are the nice points, by the way. So right, if this is 16, maybe here's 1, here's 4, and here's it's not quite that big. Here's 9. Then I'm gonna find the area of these rectangles. Still gonna be an overestimate, but it's gonna be one that's easier to calculate. So my estimate here using this non-regular partition is going to be the base is 1 times the height is f of 1. The base is 3. The height is f of 4. The base is 5. The height is f of 9. And the base is 7. The height is f of 16. That's going to give me 1 times the square root of 1 plus 3 times the square root of 4 plus 5 times the square root of 9 plus 7 times the square root of 16, which is going to be what? 28 plus 15 is 43 plus 7 is 50. Also an overestimate. All right. So let's talk about some actual real problem context. Oh, I didn't. Sure. Yeah, I kind of erased the one I wanted. Oh well, that's life. And hopefully this will help bring it back around and make some sense. So let's look at the first one we did. I know it's unfortunate that I erased it, but oh well. So here's again my function. I'm going to leave that actually for a second. And we broke it up into 4 equal sections, 16, 4, 4. And I was using upper rectangle, or I was using upper rectangles, which this is, in this problem happens to be right rectangles. So I did this, and then this. Sorry, so we were finding these areas. Okay, so here's what I want to say. Suppose that our function, instead of being f of x equals the square root of x, that's not how you spell suppose. So, suppose that we are thinking that our function is a function of time. It's still the same function, right? Still the square root of t. Suppose that that function is the velocity of some object at time t. At t seconds. In meters per second. All right. So then what does the area under the curve mean? Well, let's think about it. Our area here, well, this is now measured in seconds. And this is measured in meters per second. So when I find the area of this first rectangle, that area is the base, which is 4 seconds. Wow, not 4 divided by seconds. Come on, James. Times the height, which is the square root of 4 meters per second. And when I multiply 4 seconds times 2 meters per second, the seconds cancel and I get 4 times 2, which is 8 meters. I get distance. And write the rest of it. So the next one would be 4 seconds times the height, which is the square root of 8 meters per second. And then for the next area, I get the base is 4 seconds and the height is the square root of 12 meters per second. And then for the last one, the base is 4 seconds and the height is the square root of 16 meters per second. It's literally the same calculation we did before. We end up getting that this is approximately, what was it, 49.17. But now there's some units involved. This is 12 point something meters per second times 4 seconds gives us 49.17 meters. So if you're finding the antiderivative, aka the area under the curve, I know we haven't quite made that connection just yet, but we're going to. Right, the area under the curve, if the curve is representing velocity, the area under that curve is representing the distance traveled. So for your airplane problem, just to kind of bring it back there, if you actually drew the graph of the velocity and said, okay, I know at time 0, the velocity is 0. And I know, what is it, 10 seconds later, the velocity is like 50. And it accelerates constantly. You'd be like, hey, look, from there to there, the distance traveled is the area under the curve, which is base times height divided by 2, because it's the triangle. And then for the next part, where you go from like 50 to 300, to know it's not to scale, you can do the same thing. So like, okay, from there to there, the distance traveled is the area under that curve. It's kind of cool. You probably should do it not that way, but you can also look at it that way and see that there's this nice connection. So,
Professor, I have a quick question.
go right ahead.
So the only thing I'm just confused on is when would we pick the left points or the right points? When would do we decide to go like 0, 4, 8, or like from 4, 8, 12? You see what I'm trying to say?
Sure. And so just to be specific, if you're using left, you would use 0, 4, 8, 12. If you're using right, you would use 4, 8, 12, 16.
Yes.
It depends. It usually depends on what someone is asking you to do. So, that question, where do you get 1, 3, 5? Sure, I'll get to that in a second. Sometimes someone will say, use right endpoints, use left endpoints, use upper. So typically someone's going to be specifying what they want you to do. If someone said, estimate the area under this curve using whatever you want, I personally would always default to right endpoints because it's usually the easiest. If instead someone's asking for upper or lower, then we have to be a little bit more careful. And I'll give you a different example in just a second of how, in this example, the upper are the right and the lower are the left, but that's not always the case. To answer Roy's question, the way I got the 1, 3, 5, and 7 is by finding the distance of each partition. So this distance here from 0 to 1 is 1. This is 3. That's 5. And that's 7. Right, and find the areas. The areas of my rectangles by doing the base times the height. Base times height. Base times height. Base times height. Base times height. That's what's happening there. So let's say your function was, I'll take something not too terrible. Let's say your function is, trying to do something that's not too terrible. Sure, here's a classic. Let's say my function is 8 over x, and I want to approximate area under the curve using, on on the interval from, let's say, from 2 to, I don't know, 6, using, should we use 4 subintervals again? Yeah, sure, 4 subintervals, why not? Let's make it a little more interesting. Let's go from, I'm gonna change it just a tiny bit. Let's go from 2 to 8. And let's use 3 subintervals. And I'm specifically going to try and talk about upper and lower sums. So let's draw the picture. 8 over x looks, vaguely like this. And if I say like here's 2. So first of all, my subinterval length, my delta x, if you will, is 8 minus 2 divided by 3, which is 6 over 3, which is 2. So there's my subintervals. And I want to figure out the upper and lower estimates. Upper sum and lower sum. Is that right? Upper sum? Yeah. My upper sum, well, here, so in each subinterval, the highest point in each subinterval is the left point. So here, my upper sum is going to be given by, well, again, and let's draw the rectangles. Let me do the lower sum first because I can then draw the upper sum kind of over it. Let's do the lower sum first. So the lower sum, I want the smallest rectangle I can get in each subinterval. So there's my smallest rectangle. Smallest rectangle. Right, I'm using the right endpoint to give me the height. So the lower sum is going to be the base of each rectangle times the height of each rectangle. F of 2, f of 4, f of 6. That's going to be my lower sum, which is going to be, in this case, let's see, my base is 2. F of, I wrote the wrong thing, right? I know what I did. I said lower, my brain saw the L and I thought left. So the lower sum, right? I used 4 to find the height, so it should be f of 4. I used 6 to find the height, so it should be f of 6. And I used 8 to find the height, so it should be f of 8. That's going to be 2 times f of 4, which is 8 over 4, plus f of 6, which is 8 over 6, plus f of 8, which is 8 over 8. And this ends up being something not too terrible. That's 2 plus 1. That's 2 times 3 plus 8/6 is 4/3. I don't know. It's some number. What, like 9 nines plus 4, 9/3 plus 4 is 13/3, 26/3. And that's definitely an underestimate. Notice, by the way, that my lower sum, oh, I know, I wanted L3, not LS. My lower sum using 3 subintervals is also, in this particular case, the same as my sum using right endpoints. If I want to find the upper sum, well, then I would use the value, the input value that gave me the highest valued function. So that's going to be this. And this. In each interval, I'm using the value that gives me the highest point on interval. So in here, I'm using this point, in here, I'm using this point, and here, I'm using this point. So that means my upper sum is going to be, again, the base is 2, the height is f of 2. The base is 2, the height is f of 4. The base is 2, the height is f of 6. So there I'm going to get, let's see, 2 times f of 2 is 8 over 2. F of 4 is 8 over 4. F of 6 is 8 over 6. Here's a pro tip. If you've done one of them already, usually the other one is pretty similar. So look at this one. This one is 8 over 4 plus 8 over 6 plus 8 over 8. Or 2 plus 4/3 plus 1. This one is 4 plus 2 plus 4/3. So it's literally the same calculation, except instead of being 3 plus 4/3, it's 6 plus 4/3 inside the parentheses. So that means I know that this whole number is 3 bigger on the inside, which gets multiplied by 2, which means it's 6 bigger in actuality. And 6 is equal to 18/3. So I can say, okay, that's going to be 26/3 plus 18/3, which is 44/3. We can also do the calculation, right? This is 4 plus 2 plus 4/3. 6 plus 4/3 is 18/3 plus 4/3, which is 22/3, times 2 is 44/3. Oh, yeah, that works. Okay, so there's our upper sum. Let's do one more. One more that's going to be garbage. Now, I want to pick something symmetric. That's had an example in my mind, but I realized it's kind of too, it's almost too nice. Sure, I'm going to pick something terrible. Let's say our function is, yeah. Sorry, one sec. X cubed minus 2x squared minus 8x. And I want to find so I just want to show you why this is terrible. Maybe so here's what this function looks like. It's x. I'm gonna add on like 6 here. So here's what I've really done, just so you can see my thought process. This here is really x times x minus 4 times x plus 2. 6. So normally this part here would look like some cubic function that would go through the points -2, 0, and 4. And it would look vaguely like this. I don't know how low it gets here. Let's see, 2 times 2 and let's make this like a 16. Okay. This maybe goes as low as -16. That's not really the point. So if I shift this all up by 16, then I've got this kind of deal. So it looks kind of the same. This is the height of 16. And it looks kind of like this. And so now the question is, I want to estimate the area under this function using an upper sum. That's not going to be very fun. Here's why. Yeah, sure. I'm using, I should say, let's see, we're going from -2 to 4. Let's use 3 intervals. Let's use 6 subintervals. And I want to use upper 6 and a lower 6. All right. So here's what we've got. I'm going to try and draw this a little bit less terrible. I don't know. It's fine. So -2, -1, 0, 1, 2, 3, 4. And let's see. So the problem with this is I don't know in each interval, each subinterval, which value is going to give me the highest value. I have to actually look and see. So luckily, I know that this is equal to, I said before, x times x minus 2 plus 2 times x minus 4 plus 16. So I actually kind of need to know all my it might be really super helpful. I know it would be super helpful to use Desmos. So this is where using Desmos might be totally awesome. Check this out. So let's say we were given this problem and we wanted to estimate the upper sum. Let me show you what you can do in Desmos that might make this a little bit more manageable. Let me share my screen. Let me get some Desmos going on. So let's graph this thing. Y equal to x cubed minus 2x squared minus 8x. Cool. Plus 16. Let's zoom out a little bit. Great. And now I really want to know what's going on at each of these values. So let's make a little table. And then, oh, it even started where I wanted it to. Can I get more values, please? Cool. So great. That's showing me in each subinterval from from -2 to -1. Well, I know that at -2, the y value is 32. And at -1, the y value is actually lower. So I haven't graphed this well, but that's kind of interesting. Yeah, anyway. That's
Did you mean to put 2 negative signs?
yeah, I was like, something seems wrong there. Thanks. There we go. I was like, this seems wrong. Okay, great. So at -2, we have a value of 16. And at -1, we have a value of 21. And at 0, we have a value of 16. I know it's with the same height, whatever. At 1, the value is 7. At 2, the value is 0. Okay. So we can draw this a little bit better. Yeah, I know we should be hitting it. It's fine. At 3, the value is 1. At 4, the value is 16. So now, if we were going to find the upper and lower, so let me stop sharing. But I think that's kind of a way you could kind of figure out where it's the highest and lowest. So if I want to do the upper sum using 6 subintervals here. So each subinterval has a width of 1. So it's going to be delta x times. Let me actually write this way. And we have another problem. This is we do have a problem. And here's the real problem. If you're truly wanting to use the upper sum, you have to find the point in each interval which is the highest. And if you look back at the graph for a second, that point right there, that's not the highest point. So in the interval from -2 to -1, it actually looks like that's the highest point right there. That's a bummer. So really, if I wanted to find the upper sum using 6 subintervals, I would have to do, okay, my first one would be 1 times, there's actually some slightly higher point right here. So it'd be f of some number between -1 and -2, -1. And then plus, in the second interval, it's more clear, right? In the second interval, it's clearly going to be 1 times f of -1, which is going to be 21, plus in the third subinterval, it would be, right, so from -2 to -1, the highest point, we don't know what it is. -1 to 0, the highest point is 21, which is f of -1. 0 to 1, the highest point is f of 0. And then 1 to 2, the highest point is 7, which is f of 1. And then 2 to 3, the highest point is 1, which is f of 3. And from 3 to 4, the highest point is 16. So the thing about these upper sums is that if you've got something that's not always increasing or not always decreasing, it really, really actually takes some work to figure out what's going to give you the upper sum, the sum that is the highest overestimate you can have using rectangles. And especially finding that point right there is really kind of a pain. So what I want to say is, most of the time, this isn't an issue. Most of the time, your teacher is a reasonable person, and they give you functions that are increasing or decreasing. So if your function is increasing, the upper sum is just going to be the right endpoints. Right, I hope so too. If the function is decreasing, the upper sum is just going to be found using the left endpoints. But if you had something that changes direction like this, it's a little bit dicey to find the upper or lower sum. Now, let me give you one more example, just because I feel like none of this was a fail, but that I can give you something where we can actually calculate it. So let's do something slightly easier. Let's look at, I want to approximate area under f of x equal to 9 minus x squared on 9 minus x squared on the interval from -1 to 1 using 4 subintervals. And we will do both upper and lower sums here. So let's draw it real quick. So square root 9 or 9 minus x squared looks like this. And I'm particularly interested in going from -1 to 1. And I'm breaking it up into 4 subintervals. So first of all, my delta x is going to be my length divided by my number of subintervals, which is 2 over 4, which is 1/2. So I'm going to have these points, and then I want to approximate the area under. So for this first subinterval, if I'm doing, let's do the upper sum first. For this first subinterval, I'm going to use the right endpoint because that's going to give me the higher rectangle. So I'm going to get a base of 1/2 times a height of f of -1/2. For the next rectangle, from -1/2 to 0, I'm going to use the 0 because that's going to be the higher endpoint. And I'm going to get 1/2 times f of 0. And now for the next two, it's actually going to be kind of the same, meaning from 0 to 1/2, the higher point is the left point. So I'm going to get that, which will be 1/2 times f of 0. And then for this rectangle here, I'm going to use the left endpoint, which is at 1/2 to get the upper sum. So I'm going to get 1/2 times f of 1/2. So in the beginning, let's see, 1/2 times f of -1/2, which is 9 minus 1/4, plus 1/2 times f of 0, which is 9. And then I get those again, right? I get another 9, and I get another 9 minus 1/4. So let's see, 9 plus 9 plus 9 plus 9 is 36. -1/4 minus 1/4 is -2/4, which is 1/2. So I end up getting, see, 36 minus 1/2 is, I really don't want to write 35.5. I want to write 71/2. So I end up getting 71/4. On the other hand, if I was going to do the lower sum, L4, I would literally make the opposite choices. Since this one, it's easy to see that from here to here, it's strictly increasing. From here to here, it's strictly decreasing. If you want the upper sum, you're always going to pick one extreme endpoint. If you want the lower sum, you can pick the other extreme endpoint. So I'm going to do kind of simply, I'm going to do 1/2 times, I would do f of -1 plus f of -1/2. And then here I would do f of 1/2 and f of 1. So that would give me 1/2 times f of -1 is 9 minus 1, which is 8. F of -1/2 we already know is 9 minus 1/4. And then we get another 9 minus 1/4. And we get another f of 1, which is 8. The insides here are literally just 2 less than the insides there. So I get 1/2 times 71 halves minus 2, which is minus 4 halves. So that would be 67 halves. So I get 67/4. Not too shabby, right? I mean, our answers are not too far apart from each other. They differ by like 1. Yeah. So upper sums, lower sums, kind of a pain in the butt. Right and left sums are much better in that they're easier. But you shouldn't stress too much about it. You'll have to deal with it for a little while at the beginning of the quarter, and then it'll kind of just go away. We'll never talk about it again. Let's see. Oh, then I was going to address the question from Roy, I believe, which was what if, so the question was, in case you guys forgot, sorry, it's up here. What if you're not given a function, but a table and no interval? So, and I believe that the context of that was how to like estimate the area essentially, or estimate the distance traveled. So let's look at, I feel like all these, so I'm looking in the book here, and all these examples are almost too nice in that all of your time intervals that they're giving you are uniform, which is kind of almost too easy, but fine, we'll do that anyway. So I'm looking at, we have to deal with what a lot, Daniel? The having a table. So I think Roy's question was that we are given a table and then we're not given a function. And I would say it depends. Probably not a whole lot.
Wait, James, could you turn it around just for a quick sec?
Sure.
36. Okay, thank you, James.
You're welcome. So let's say we're given the following information. We know that, fine, so we're given the following time and velocity information of a car. We know that and time is measured in seconds. Velocity is measured in, feet per second. So here's our time. So times 0, 10. It increases by 10 every time. So 2 minutes worth of time, it looks like. And we're also given the speeds. So times 0, the speed 0, and then 44 feet per second, and then 15, and then 35, and then 30, and then 44, and then 35, and then 15, 22, 35, 44, 30, and 35. By the way, this is problem 11 in the section 5.1 in your textbook. So the question here, now I will point out that the question here does specifically talk about left endpoints versus right endpoints, but maybe I'll make it upper and lower. So it says, here's the context. You and your companion are about to drive a twisty stretch of dirt road in a car whose speedometer works, but whose odometer, mileage counter, does not. To find out how long this particular stretch of road is, you record the crest velocity at 10-second intervals, with the results shown in the accompanying table. Estimate the length of the road. So let's do it using upper, lower, right, and left. So using right endpoints. So I'm going to say this is R12, right? Because there's literally 12 pieces of it. There's 12 endpoints, right? So right there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 data points, but that means we have 12 subintervals. So if I'm using right endpoints, I'm just saying, okay, so my distance traveled is velocity the change in time times the velocity. So that's going to be, well, each subinterval, the change in time is 10 seconds. And so in this first subinterval from 0 to 10, I'm going to estimate the velocity to be 44 feet per second. And in the second interval from 10 to 20, I'm going to estimate the velocity to be 15. So right endpoints, I'm literally just using the right endpoint, right? From 0 to 10, I'm using that one. From 10 to 20, I'm using that one. So it's going to be 44 plus 15 plus 35, right? It's a little bit terrible, but it's literally just right endpoints, which we could calculate, right? I mean, we can get, right? And it's not that hard to calculate. 44 plus 15 plus 35. I think someone might be unmuted who doesn't mean to be. All right.
Sorry about that, James.
Oh, it happens. No problem. So calculating this. Wow, okay, it's done. So, and again, right, this is in feet per second. So I end up getting 10 seconds times what they here 384 feet per second, which ends up being 3,840 feet. So that's our estimate using right endpoints. But we could also estimate it using an upper sum. So the upper sum says for each interval, you pick the highest value. Now, since we only know the values of the endpoints, those are the only things we have to pick from. So that's going to be, again, each subinterval has a length or delta t of 10 seconds. So first subinterval, I'm picking 44. Next time, I'm also picking 44, right? First subinterval, 44 is the highest. Second, 44 is the highest. Next one, so basically each pair, you're going to pick the highest thing. So for this one, I'm going to pick 35. For this one, I'm also going to pick 35. For this one, I'm going to pick 44. For this one, I'm also going to pick 44. For this one, I'm going to pick 35. For this one, I'm going to pick 22. For this one, I'm going to pick 35. For this one, I'm going to pick 44. For this one, I'm going to pick 44. For this one, I'm going to pick 35. It's going to give us a very large overestimate. So if we do this one, let's see. I got 44, 1, 2, 3, 4, 5, 6 times. I have 35, 1, 2, 3, 4, 5 times. And then let's see, what else do I have? I have a 22. Is that it? I feel like that does not feel like enough data points. 6, 5. How did I? I've definitely missed some because there should be 12. Let's double check. Let's see. I had a 44, a 44, a 35, a 35, a 44, a 44, a 35, a 22, a 35, a 44, a 44. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How is my brain not counting this right? Because I'm really smart, because I can't add 6 and 5. That's yeah. It's got the right number of things. Now we have it right. My brain was just 6 and 5. I somehow was getting 9 because I'm really brilliant. Okay, so anyway, when you do this, you get 461 times 10, right? So it's really a lot more. So that's going to give us 4,000 610 feet. A big difference. How do you get the delta t? So the delta t, so each time, so you're measuring the time every 10 seconds. You're measuring 0 seconds and 10 seconds and 20 seconds. So the delta t is just the difference between each of these times, which happens to be 10 every time. And all of these examples, the delta t or the delta x, whatever that is, always ends up being the same, which isn't super realistic, but it is what we've got. We can also do the left. So if you did the lower sums, you do the same thing, except you pick all the lesser values. So let's do the lowers real quick. So the lowers would be 10 times, let's see, 0, 15, 15, 30, 30, 35, 15, 15, 22, 35, 30, 30. So doing it that way, just to see the contrast, you would get, let's see, 15, right. Okay, 30, 30, 30 is 90, 125, 140, 155, 190, 220, 250, 272. Times 10 is 2720. So, right, I mean, depending on the method you use, you're getting a lot of different answers. And then if we use left endpoints, left endpoints would probably be a lot closer to the right endpoints. In fact, we can do, so the left endpoints we can actually do really, really easily. We want to do left. So here's the nice thing about left endpoints versus right endpoints. The left endpoints are the same numbers as the right endpoints, except instead of using this value, we use this value, which just makes it 35 less than it was. So if we take this value and subtract 35, we get 384 minus 35, which is 349. So you get 3,490. So upper and lower sums are going to give you more extremes usually, whereas right and left are typically a little bit more in the middle. Again, if your function is always increasing or always decreasing, then left and right will correspond to lower and upper depending on if it's increasing or decreasing. But if you got something that's like the values keep going up and down, upper is really going to catch all the highs and lower is going to catch all the lows. And so you're going to get kind of a lot of divergence there. All right. So why are we doing all this? Well, because what we would really like to do is to be able to talk about the actual amount of area under the curve, not an estimate, but the actual area. To do that, we need to build up a little bit of mechanics, a little bit of machinery, actually, what I meant to say. So let's go ahead and we're gonna kind of move in a different direction for a moment here. So let's talk about sigma notation, which is really just a convenient notation for what we've been doing, really. For example, just to kind of bring it back to, say, that first example where my function was the square root of x on the interval from 0 to 16. And I wanted to estimate the area under the curve using right endpoints. So I wanted to find, like I was trying to find or get that using right endpoints, I'm just going to say right, that the area was 4 times f of 4 plus 4 times f of 8 plus 4 times f of 12 plus 4 times f of 16. That's kind of a pain to write out. And there's actually a much more convenient way to write it. Oh yeah, it was number 11 in section 5.1. Yeah, which I don't know the page number. I think it's page 309. But there's another way to do this. I can write this as the sum from, you use I, K, so people use I, so use K, doesn't really matter. From K equals 1 to 4 because I have 4 things. So I need 1, 2, 3, 4 of 4 times f of 4k. This gives me exactly the same thing. I start at k equals 1, and I plug in 1 for k. So I get 4 times f of 4 times 1. And then I iterate and I go up to the next integer, which is 2. I plug in 2 for k. First I add, then I plug in 2 for k, I get 4 times f of 4 times 2. And then I plug in 3 for k, I get 4 times f of 12. I plug in 4 for k, I get 4 times f of 16. This is so much nicer to write. We try and do this a lot. So let's talk a little bit more about how the sigma notation works and kind of the ways in which we can manipulate it.
Wait, James, could you re-explain that one more time? The sigma notation.
Sure. Well, let me explain it with another example. So the whole idea of sigma notation is it's just a compact notation for a sum of things. So for example, if I wanted to express, or if I wrote the sum from say k equals 1 to 5 of 3k plus 2, here's what this means. It means you're going to let k equal each of the values between each of the integer values between 1 and 5. So I'm going to say first k equals 1. So literally plug in 1 for k. And we're going to get 3 times 1 plus 2. It's a summation, so it means we're adding stuff up. So in the next one, we're going to plug in 2 for k. We're going to get 3 times 2 plus 2. I'm done with that one. So now I move on to the next integer, which is 3. I plug in 3 for k. I get 3 times 3 plus 2. I move to the next one, plug in 4 for k. I get 3 times 4 plus 2. And then finally, I get to the last one because I'm stopping at 5. I get 3 times 5 plus 2. Now, we could add all this up, but honestly, I don't actually really care what this adds up to. What I actually care about is showing you that this also can be simplified in another way. So notice I can group, if I want to, all of these things together. I could write this as 3 times 1 plus 2 plus 3 plus 4 plus 5. And I could also write it as the other part. I have a 2, 2, 2. I have 5 2s. And I could write this up. I could rewrite this as 3 times the sum. 1 to 5. Okay. Okay, so that's literally what that is. That's 1 plus 2 plus 3 plus 4 plus 5. That's the sum from k equals 1 to 5 of just k. And this here is the sum from k equals 1 to 5 of 2. You're just adding it, right? There is no place to put the k, so you're just getting 2 plus 2 plus 2 plus 2 plus 2, which is exactly what that is there. But the point of this is that you can break up a summation and pull out constant multiples. So when I see the sum of things added or subtracted together, I can say like, oh, I'm going to write that as the sum of 3k plus the sum of 2. And then I'm also going to pull this constant multiple out in front. Now you might wonder, well, how is this helpful, James? I don't know how to add up k 1, 2, 3, 4, 5, right? Or maybe if we were going to like 100, right? We need to know how to add those up. Yeah. So.
James, I have a quick question.
Go ahead.
So how did you know that we had to get 5 numbers? Like, why 5?
Because we're starting at 1 and we're ending at 5.
Oh, I didn't see. Yeah, of course. Okay.
Now I will say, so the number of things that you get in a summation is always one more than the difference between the starting and the ending place. So 5 minus 1 is 4, 4 plus 1 is 5. So just as another example, if I was going to talk about, say, finding the sum from k equals 3 to 6 of, I don't know, 4k squared plus k, I know that there's going to be 6 minus 3 plus 1. That's 3 plus 1, which is, there's going to be 4 terms. I'm going to start when k equals 3. So I'm going to get 4 times 3 squared plus 3. Plus, now I'm going to let k equal 4. I'm going to get 4 times 4 squared plus 4. And then I'm going to let k equal 5. 4 times 5 squared plus 5. And then I'm going to let k equal 6, which is the last thing k gets to equal because that's what that tells me. And again, I totally could have broken this up as 4 times the sum from k equals 3 to 6 of k squared plus the sum from k equals 3 to 6 of just k. Right? Here's my 3 plus 4 plus 5 plus 6. That's this. And I'm running out of colors. Sure. And here's my 3 squared plus 4 squared plus 5 squared plus 6 squared, which is this, all times 4. But again, the question remains, how does breaking this up into these things help us? Well, there are actually formulas for these things. So there's probably 3, maybe 4 formulas you're going to want to know. Now, I will tell you.
James?
Yeah.
Could you once again flip the whiteboard just real quick?
I will tell you that the formulas I'm about to talk about, although they are useful in other places, we really mostly only use them in this section here. So, good to go?
Yeah, thank you, James.
So, let's talk about them. The first one is not too bad. If I want to find the sum from, say, like k equals 1 to n, right? So n could be any natural number of a constant, say like 6. Well, that just means I've got 6 plus 6 plus 6 plus 6 n times. Well, that's just 6 times n. Or more generally, the way it's usually written is the sum from k equals 1 to n of 1 is equal to n. And the sum from k equals 1 to n of a constant is equal to, well, again, we can factor out constants. So that's just the constant times the sum from k equals 1 to n of 1, which is just c times n. Okay, those are pretty straightforward. The next one is pretty cool. I'm not gonna lie, I think this next one is pretty neat.
James?
Yes.
I'm sorry, once again, could you flip the whiteboard again? Okay, thank you, James.
So the question is, how do we find the sum from k equals 1 to n of k? Which is 1 plus 2 plus 3 plus 4 plus all the way to like n minus 3 plus n minus 2 plus n minus 1 plus n. Well, there's a really, really slick way of doing this. I'm going to add it to itself. Now check this out. I'm going to add the sum again. So I know that when I add this together, I'm going to get double. Now here's the tricky part. It's not even tricky. Here's the kind of slick part. I'm going to write this, but I'm going to write the sum in the opposite order. So I'm going to write it as n plus n minus 1 plus n minus 2 plus n minus 3 plus all the way to 4 plus 3 plus 2 plus 1. Okay, so now we're going to add these together and we're going to add them column-wise. So when I add this to this, n plus 1 is n plus 1. When I add this to this, okay, somebody help me out. What's n minus 1 plus 2? You could type it in the chat.
It'll be 3.
Not quite.
1 plus 2. Oh, my bad. N minus 1 plus 2. It'll be n1.
N
Plus 1.
plus 1. Okay, what about n minus 2 plus 3?
N plus 1.
Oh, n plus 1 again. How about n minus 3 plus 4? Oh, n plus 1 again. Another key. So here's the thing. Each of these things we add together end up being n plus 1. Let me ask you guys, how many things did we add together?
4.
How many terms were there? How many terms were there? Yeah, n, exactly. So look, you're adding the same thing up n times. That's going to be n times it. Right? If you add up 6n times, you get 6 times n. If you add up n plus 1 n times, you get n plus 1 times n. So then, if I want to find a formula for that, divide by 2. And that's the formula for the sum of the first k integers. So if I wanted to say, you know, like what's 1 plus 2 plus 3 plus all the way to 100, I could be like, hey, it's 101 times 100 divided by 2, which is 101 times 50, which is 5,050. Not that we really need to do it for a specific number, but one could. So this formula is something we're going to use. We'll use it next week for sure. Let me show you the other two formulas. The other two formulas that we may need to know are not. Oh, attendance, good call. I do need to take a screenshot. Thank you. Let me grab a screenshot. If I ever miss your attendance, like if you get marked absent and you shouldn't have been, just let me know and I'll probably go double check the Zoom log just to be absolutely sure. Not that I think it was a good line to attendance, but I'll check anyway. And then I'll be like, oh yeah, I'll fix it. But yes, but also good to remind me to take attendance because it just makes my job easier if I do that. So let me show you the other formulas, which are also pretty slick. So the sum of the first n squares, so 1 squared plus 2 squared plus 3 squared plus all the way to n squared, which we could write as the sum from k equals 1 to n of k squared is n times n plus 1 times 2n plus 1 over 6. And then the sum of the first cubes, there's actually something really, really cool about this. So 1 cubed plus 2 cubed plus 3 cubed plus all the way to n cubed, which is the sum from k equals 1 to n of k cubed. Check this out. I could write this in a confusing way, but I'm going to write it in the way that anybody writes it. It's n times n plus 1 over 2 quantity squared. Hey, look, that's a familiar formula. That's not. Here is what I think is one of the neatest things in math, really, ever, is that if you add up the first n cubes, it is the same as adding up the first n numbers and then squaring the result. So, for example, 1 cubed plus 2 cubed plus 3 cubed is equal to 1 plus 2 plus 3 squared. It's true. 1 plus 8 plus 27 is 36. 1 plus 2 plus 3 squared is 36. And it works no matter how many numbers, right? If you go to the next one, true. 1 plus 8 plus 27 plus 64 is 100. And 1 plus 2 plus 3 plus 4 squared is 100. So I just think that's kind of super neat. It's also a formula we're going to use. So I'm not just saying it because it's neat. It's also because it's important, but it is really neat. So yeah, these formulas do come up. We will use them next week when we start actually trying to show the area under a curve, not approximately, but exactly. And we're going to do that by using more rectangles. So we're going to take our example using just a few rectangles, and we're going to let the number of rectangles increase to infinity, so that we're going to end up taking a limit as n goes to infinity of this sum of areas of rectangles. That's kind of the big picture. We're going to take these approximating sums and make them exact by taking the limit. All right.